Hello, welcome back to Discrete Mathematics and its applications on the topic of relation. Last time we stopped here. Uh, this is an exercise and we'll discuss the answers. But before that, if you're not done with answering these questions, pause the video and try finishing this exercise first. If you're done, then we could continue. So let's answer the first one. Given the set above, what is b times a? Well, b times a should be the pairs a, 1, a, 2, a, 3, and the pairs b, 1, b, 2, b, 3. So you have 6 pairs. What about b times b? Well, b times b consists of the pairs whose elements are taken from b, all of them. So all possible combinations of them give you the pair a, a, b, b, a, and of course b, b. 4 pairs. Now how about b times c times a? Well, this consists of triples, and you take triples from b, from c, and then from a. So you take from b, which is the letter a, and from c, which is the integer 0, and from a, which is the integer 1. And then we continue a, 0, 2, a, 0, 3. And a, 1, 1, a, 1, 2, a, 1, 3, b, 0, 1, b, 0, 2, b, 0, 3, and b, 1, 1, b, 1, 2, and b, 1, 3. So you have 2 times 2 times 3, which is 12. So you have 12 triples. Now how about a times b times c times d? So for a times b times c times d, we want to form 4 tuples or quadruples, where the first element of the 4 tuple is from a, the second is from b, and the third is from c, and the fourth is from d. However, d is actually the empty set, so there is no way we could take any element from it. So therefore, a times b times c times d consists of no 4 tuples, or in other words, a times b times c times d is simply the empty set. So how about it? Did you check your answer? Hopefully everything is correct. Now we're done with this, and we will continue with the definition of relation. So let capital A1, capital A2, capital A3, and so on up to capital AN be sets. Then an n-ary relation R over those sets is a subset of the Cartesian product A1 times A2 up to times AN. So a relation, an n-ary relation, is a subset of the Cartesian product of the n underlying sets. Now, because of that, we usually write n-ary relation R using subset notation like this. Now, the sets A1 up to AN are called the domain of the relation R, and N itself, which is a natural number, is the arity of the relation R. Now, given a relation R, we could say an n tuple a1, comma a2, comma and so on, comma an is an instance of R if and only if that tuple is an element of R. Remember, R here is a set because it is a subset of the Cartesian product. Now, if the n tuple a1 up to an is an instance of R, then we also write it this way. Yeah, R and then the tuples. If R is binary, that is when n is equal to 2, then an instance a comma b is an element of R, could be written ARB. So the previous example of divisible by relation, we could simply also write 12 divisible by 4. Now, this is a formal definition of relation. So to give you more understanding, let's have a look at some examples. But before that, let's try answering these questions first. First, can a relation be empty? And the second is, can a relation be infinite? Now, for the first one, remember, a relation is a subset of a Cartesian product, and there is no other restrictions on that. So therefore, because a subset of a Cartesian product could also be empty, therefore a relation can be empty. Yeah, because empty set is also a subset of the Cartesian product. Now, can a relation be infinite? Well, relation is a set, and it is a set of n tuples. Now, the set of n tuples becomes infinite if the underlying set is possibly to be infinite if one of the underlying set is infinite. So that is if any of the domain set, so any one of capital A1 up to capital AN is infinite, then a subset of the Cartesian product may also be infinite. So relation can be infinite. Now, for n array relation like n tuples, we have n ranging from 0, 1, 2, and so on. So if n is equal to 0, then we have a trivial nullary relation. It's called nullary. Yeah? And this contains only the empty tuple. So a set that contains exactly one element, and that element is the empty tuple. And this relation is called the nullary relation. There is only one of these. Now, if n is equal to 1, then we call the relation unary relations, which is equivalent to sets of non-tuple objects. Remember, a one tuple could also be written without the parenthesis. So therefore, say an example of that would be the relation R that contains one tuple that contains an integer 0, one tuple that contains an integer 1, and one tuple that contains an integer 2. So you have 3 one tuples, and omitting the parenthesis gives you simply a set containing 0, 1, and 2. Now, if n is equal to 2, then we have binary relations, and binary relations are sets of pairs, and this is our focus of this chapter on relation. Now, a binary relation R over A and B is also called a binary relation from A to B because, well, it involves pairs and the tuples indicates direction. So from A to B. Now, if A is equal to B, then the binary relation R over A times A, well, is simply called binary relation over A. Now, if n is equal to 3, then we have ternary relations or sets of triples. If n is greater than 3, then of course sets of n tuples. Now, in general, n-ary relations are used in computer science in the field of relational databases. You will study this in a later course. So, in relational databases, n-ary relations are used to model data. Now, let's have a look at a concrete example. Suppose A is the set of cities or towns in Java that are headed by a major, and B is the set of Indonesian provinces in Java. So define a relation R such that the pair A comma B is in R if city or town A is located in the province B. Now, in addition, try giving examples of pairs in the Cartesian product A times B, but do not belong to R. So, how do we solve this problem? Well, first, let's identify the set A and the set B. The set A contains cities, and the cities must be headed by a major. Simple lookup in Wikipedia or Google could give us the fact that A contains 34 cities. For example, Cilegon, Jakarta Pusat, Depok, Bandung, Semarang, Magelang, Surabaya, Malang, and so on. So you have 34 cities in Java that are headed by a major. Now, how about the set B? B contains, well, this could be counted by hand, contains 6 provinces, namely Banten, DKI Jakarta, Jawa Barat, Jawa Tengah, DI Yogyakarta, and Jawa Timur. Now, to define a relation R, let's define the Cartesian product of A times B first. Now, A times B must contain, of course, because A contains 34 elements and B contains 6 elements, therefore A times B contains 34 times 6, which is 204 pairs. Now, among these 24 pairs, only 34 pairs that actually belong to R. So here, for example, Cilegon and Banten is an instance of R because Cilegon is located in the Banten province, or Cirebon and Jawa Barat is a pair in R because Cirebon is located in Jawa Barat, and so on. So you have 34 pairs of this. Now, what would be examples of pair in A times B that do not belong to R? Well, there are many of them. For example, the pair Bandung Jawa Tengah, which is a valid pair in A times B, but this does not belong to R because Bandung is not located in Jawa Tengah. Similarly, Madiun, Jawa Barat is a pair in the Cartesian product, but do not belong to R because Madiun is not located in the province Jawa Barat, and so on. So, to test your understanding, let's do one other exercise. So here we have 3 questions. The first one, you have to give 2 examples of binary relation from A to B, where A and B are given there, and count how many such relation are possible. In other words, given A and B, how many possible relations could be formed over these two sets? For number 2, you are given 5 pairs of integers, 1, 1, 1, 2, 2, 1, 1, minus 1, and 2, 2, and check if all of these 5 belong to the relations given below. So R1, R2 up to R5. R1 is a set of pairs from Z times Z, such that A is less than or equal to B. R2 is a set of pair A, B, such that A is greater than B, and so on. Now, number 3, there are 3 ternary relations given here, R1, R2, and R3. Now, for each of these 3, write its degree and domains, and give 2 triples that belong to it, and 2 that do not belong to it. So for each of R1, R2, and R3. Try solving this exercise first, and we will discuss the answer in the next video.